Hello everyone, today is another day of learning new things about math. We are the group 5 and my name is John Ashley.
And my name is Paul.
And my name is Jose.
My name is Jan.
I am Peter.
And I am Eliza.
Ever wondered how musical instruments make sounds or symphonies and melodies?
Do you know how televisions operate? Have you ever pondered how several scenarios and channels can be displayed on a single screen?
You might be surprised to learn that mathematics enables all of them.
Let's explain by talking about chapter 5 of Ian Stewart's book Nature's Numbers from Violins to Videos. The goal of this book is to give us a mathematician's eye, altering how we see the world.
This chapter begins with the narrative of how applied mathematics and pure mathematics came together to produce something more potent and engaging than either of the two could have produced on their own. And it started with the issue of a vibrating violin string at the beginning of the 16th century. Vibrations result by plucking a single violin string. The Greeks believed that the manner in which the violin string is plucked affects the way it vibrates.
Later on, it was discovered that the frequency of vibrations determines the pitch of the violin's tone.
An English mathematician named Brooke Taylor wrote a work in 1714 that described the length, tension, and density of the fundamental congressional vibrational frequency. The moving string can assume many distinct shapes, and each frequency corresponds to a different configuration of a string.
This great concept was demonstrated by a demonstration of how the violin's pitch is influenced by the notes.
This chapter demonstrated to us how single strum of violin string could start a series of inferences and discoveries. In reality, Jean Leron D'Alembert was the first to assert that the wave shape might be anything but.
However, in reaction to D'Alembert's research, Lionheart Euler developed a wave equation. The results of the study of Euler and Bernoulli shows that the sinusoidal wave that gave rise to the wave equation is one of the basic vibrational components.
The vibration of a violin string was responsible for the initial introduction of the wave equation, and the drum was the next instrument to contribute to a more accurate formula.
Moving away from the instruments was the next series of events, and it resulted in the discovery of the equation known as the most significant mathematical formula, which is Einstein's well-known link between mass and energy. And the application of this formula to electricity and magnetism was a major game changer.
Electricity and magnetism captivated the attention of Michael Faraday. He was aware that an electric current would hold a magnetic force and that an electric current could be generated by a magnet.
He therefore succeeded by 1831 and demonstrated that magnetism and electricity are two components of electromagnetism. James Clerk Maxwell, Faraday's successor, utilized a mathematical equation in the future to describe the dispersion of magnetic and electrical change in space.
So, by 1864, had reduced his theory to four differential equations: Gauss' law for electric fields, the corresponding formula for magnetic fields, Faraday's law of magnetic induction, and Ampere's law plus Maxwell's displacement current. The distributions of electric charges and currents that result in electric and magnetic fields, as well as how those fields vary over time, are described by Maxwell's four equations. They were the result of Michael Faraday's strong equation and techniques of experimental investigations on the effects of charges and currents on electric and magnetic fields. Even though Maxwell's contribution to this equation is only on the final term of the previous one, its addition had significant effects. It provided the first concrete evidence that magnetic and electric fields may interact with one another. These fields might continue to spread throughout space indefinitely, or from the fluctuating charges and currents that give rise to them.
Hence, these four theories reveal the curious symmetry between electricity and magnetism, each affecting the other in a similar manner.
Furthermore, it was indicated by the wave equation that the electromagnetic waves moved at the speed of light. For instance, Heinrich Hertz created the radio when he was able to produce electromagnetic waves at the appropriate frequency. Televisions and videotapes followed, and the rest is history.
The division of mathematics into pure and applied categories has long been done. The greatest mathematicians of all time were baffled by this categorization. But to them, math is math. The historical overview of how their contributions have benefited us in every facet of life is fascinating.
The developed equation, which proved to be helpful in mapping electricity and magnetism, was inspired by a great experience. And that's how mathematics might start out as something we might consider as simple in life, but end up becoming a succession of complicated yet significant discoveries.
That would be all. Thank you for watching. Hope you learned something. Until next time.